Hello everyone and welcome back once again in the class of fundamentals of particle and fluid solid processing. We were discussing about the pneumatic transport that we introduced in the last class. We have seen two different flow regime, that is the dense phase flow and the dilute phase flow, how to demarcate between these two in case of horizontal flow and the vertical flow by determining the choking velocity and the saltation velocity. Now we will see a more generic description that how to calculate the pressure drop. So before that, let's introduce some of the known parameters that we know, but still say to refresh our memory, few definitions which will govern the transport of the solid and the fluid, in this case the gaseous phase. So usually we say the superficial gas velocity, which is designated as UFS, is the volumetric flow rate of gas divided by the cross sectional area of pipe. Superficial solids velocity, similar to that, we have volumetric flow rate of solids divided by the cross sectional area of the pipe. Now say this solids concentration or the amount of solids, once it is there in the system, the void space that is occupied by the gas phase is epsilon. That is the void edge of the bed, because that is the empty space that the gas phase can occupy and can flow through those area. So that means the fraction of flow rate available for solids to flow is 1 minus epsilon, and then the actual gas velocity is the superficial velocity divided by the porosity or the void edge, respective void edge, if I say the respective volume fraction. These are the relations we knew, or even if you look at the actual gas velocity expression, it is the flow volumetric flow rate of the fluid divided by the area which is available for that fluid to flow. The area available for gas phase to flow is A epsilon, the area available for solids to flow is A into 1 minus epsilon. So that these are the actual velocities, or in other words, the relation between the actual velocity and the superficial velocities are these. That is, the superficial velocity divided by the void edge or the respective volume fraction is the actual velocity. So in most cases, the common nomenclature that is followed in fluidized bed or in this kind of transport, that U typically says it is the superficial gas velocity. So if you remember that, maybe the coming up the forthcoming slides will be mentioning this, the superficial velocity, as simple U. The mass flask of the solid that we have seen its nomenclature as G in the last class as well, which is the mass flow rate of the solids divided by the cross sectional area of the flow. Now there would be the relative velocity between the particles, the solid particles in suspension, and the air or the gas phase. That if we say as the relative velocity, then it is defined as UF minus UP, which is also popularly called as the slip velocity. We say this is the U slip. Now in case of vertical arrangement of the dilute phase transport, the slip velocity is mostly or very often assumed to be equal to that of the single particle terminal velocity. It helps us to estimate several parameters. Now if we write the continuity equations, then we see that for particles the mass flow rate of the solids is this value, that the cross sectional area, its available flow area multiplied by the actual velocity multiplied by its density, or you can think of in this way that the cross sectional area multiplied by the superficial velocity multiplied by the density. This whole parameter is basically the superficial velocity, because if you look at this expression, the superficial velocity is actual velocity multiplied by 1 minus epsilon. So, similarly for the gas phase, the mass flow rate of the air or the gas phase, we can write this expression. So, the parameter solids loading is the ratio of the mass flow rate of solids to the mass flow rate of air, which is defined as this. Now, if we look to derive an expression for the pressure drop, because this is what is important, we have seen in case of slurry transport how to estimate the pressure drop in the case of dilute phase transport. Now, here if we consider the similar scenario and irrespective of its orientation, so a generic approach can be something like this, that say the area available for cross section, this flow, the cross sectional area is A. We take a pipe section of length delta L. UP is the particle velocity, UF is the fluid velocity. These are the actual velocities. So, there would be the pressure difference of delta P, and this section is inclined with the horizontal plane with the angle of theta. So, we try to now write the pressure drop expression for this entry, this inlet and the outlet. So, if we now try to write this, the essence is that the momentum equation for this section of the pipe is basically the net force that is acting on the pipe content is the rate of increase in momentum of that content. This is the balance we write for the momentum equation. So, net force that is acting on the pipe content and which is equals to the rate of increase of the momentum of the content. Now, the net force that is acting on the pipe content is the pressure drop minus the frictional forces and the gravitational forces. So, the frictional forces are the gas and wall friction force, solids and wall friction force, as well as the gravitational force. This is the net force that is acting on that element or the content that is that dl length and the cross sectional area A of that pipe section, which is equals to the rate of increase in the momentum of gas and the rate of increase in momentum of the solids, because the content is basically the gas and the solids particle. So, we can individually write this rate of increase for both the cases. So, now if we try to write each and every element, each and every component is shown here, the respective part, where this capital F and small fw is the gas to wall friction force per unit volume, that is multiplied by the volume amount gives us the frictional force due to the gas and wall interaction. So similarly, all the components can be explained. This PW stands for the particle and wall, or the solids and wall friction, this force per unit volume. So by doing so, and this is the gravitational force that is acting on the gas and the solid content, which is the rate of increase of the momentum of gas plus the rate of increase of momentum of solids. Assuming the gas density remains constant and the voidage remains constant, if we integrate this expression, we can find the del P, or the P2 minus P1, P outlet minus P inlet, and that expression would be something this one. Where we have all the individual component on the right hand side explained, that the first term is the pressure drop due to gas acceleration. Second term is the pressure drop due to particle acceleration. Third term, the pressure drop due to gas or the fluid and the wall interactions or the friction. Fourth term, pressure drop due to the particle wall friction. Fifth term is the pressure drop due to static head of the solids, and sixth term is the pressure drop resulting from the static head of the gas or the fluid. So these are what we also started with, and this we can see that it is indeed the case. Now this expression can be applied for any pipe transport irrespective of its orientation, provided we know these friction forces, these two. That means the gas wall friction and solid wall friction, because other quantities we typically know from the operating condition or from the measurement. So depending on these two values or analysis of these two values, we can apply it for any orientation of the pipeline network having this pneumatic transport, or even we can apply this kind of balance for the slurry transport as well. So now the point comes that how to have this dilute phase transport efficiently. So it is always desirable to operate that with the lowest possible velocity to minimize the frictional pressure drops, to reduce the attrition, to reduce or to minimize the running costs. And for any particular size or the solid size and the fixed pipe diameter, the saltation velocity is always higher than the choking velocity. So which means we have to avoid, so when we construct the pipeline network that would consist of horizontal component as well as the vertical component, so several pipeline networks will be formed, that this phase is coming here, going there, some phase is coming here, it is combined, again flowing in horizontal direction, again going in the vertical direction. So when this kind of network is there, the pipeline network, while selecting the appropriate operating velocity, we have to remember this scenario. saltation velocity occurs in horizontal case, choking velocity occurs in vertical case. So, which means we have to avoid by any cost this saltation velocity. We have to operate this on the higher side of the saltation velocity, so that both the velocities can be taken care of, or we can avoid the choking velocity for obvious reason. Now, in case of dilute phase transport, this gas to wall friction is often assumed to be independent of presence of the solids, because while calculating or analyzing these two parameters, the consideration has to be made that whether this gas wall friction is dependent of the solid particles or not, or the presence of the solid particles or not. So, in case of dilute phase transport, this is assumed to be independent of the presence. And then again, there are several correlations available to find out what is those friction forces that the particle wall as well as the gas wall frictions. Now, in case of dilute phase transport, as it is compared to be considered to be independent of the solids that is present there. So, in vertical transport of this dilute phase thing, so we have these expressions from the literature, and in case of horizontal transport, we have this expression when this equation is expressed in terms of mass flux, it reduces to this expression. So, from this expression we can find out that what is the particle wall friction force in case of vertical as well as in case of horizontal transport. Now, here this UP has to be calculated, and that also comes from this correlation, where again if you remember we mentioned that U is the superficial velocity, UP is the particle velocity, actual velocity, because these are difficult to determine. We can easily determine the superficial velocity, but not the actual velocities. So, this is what is given in such case, and we can find out the friction factor for such case, where CD is the drag coefficient between the particle and the gas phase. So, the point is that there are several correlations and we have to choose appropriately or in a suitable manner that fits our working condition that we have mentioned or emphasized during the slurry transport calculations as well. Similar to that, here also we have to apply the similar strategy. Now, in case of transport in a pipeline network, it is desirable that there would be as few bends as possible. If we now consider that we know everything, now it is being transported, this dilute phase is being transported. So, there has to be as few bends as possible, because these bends would create more pressure or create the requirement of more pressure drop. So, and these bends also creates the detrimental effect to the velocities. For example, there is a greater tendency of the particles to settle or salt out in a horizontal pipe that is preceded by a downflowing vertical to horizontal bend. So, such say if a pipeline network is something like this, the particles are coming like in such a manner, or even in the other direction you can think of, the flow is happening something like this. So, the solid particles will be salting here for a longer period. In such cases, or even here, when it comes, it would try to settle here, or in fact would settle, and it would take a longer time to again coming back to the circulation loop. So, it is to be avoided. Now, earlier it was thought that gradual or say a slope wise change in the bend would help in reducing the attrition or erosion of the pipeline, because this gas and the particles are flowing at a very high velocity. But it has been seen by thorough research that use of blinded tees in place of elbows greatly reduces the lifetime of a pipeline network. For example, so this is the example of a blinded tee in place of just an elbow. So here what happens, the effect of cushioning is imparted to the oncoming solid particles. So some solid particles are gathered in this blinded section, dead end section. So particle cushioning effect happens. So direct hitting of this wall while it is flowing in this direction, this changes its direction, the attrition, the corrosion, all these things is reduced and greatly reduced. The lifetime becomes in order of magnitude higher than a simple elbow. So such kind of design consideration are there, but there is no hard and fast rule for that. This comes from the experience, the previous experience, the design experience from the operators. Now, typically a thumb rule is that the bend pressure while designing a pipeline network, as the bends cannot be avoided, but how to then estimate the overall pressure drop through the network. A typical guideline is that the bend pressure drop would be almost equivalent to 7.5 meter of a vertical section pressure drop with the same kind of particles, and this is then added with the straight section of the pressure drop calculations, because this bends, elbows and all these parameters are the practical fittings of a pipeline network. So several such design consideration has to be made in order to have an efficient design of this pipeline network that would be carrying this pneumatic transport. Now, like in slurry transport, we have seen that how it is typically flown or how it is typically conveyed. One of such schematic for the pneumatic transport is shown here. So here these are the solid particles are stored in a storage hopper, and this is a rotating air lock is there. This is the conveying line. Here the blower is there from where the air comes and being pushed in the conveying line along with the solid particles that carries. And at the receiving end of this suspension, it is filtered using different types of filter that we have seen, and then the particles goes to the process after collecting the particles. So it is not that one single stage operation of the filtration can help in separating this suspension. There can be multiple stages of separation, or the loop it can goes again and again, not the single pass operation. So all these actually constitute the whole dilute phase transport line. So then these details you can find it again in the encyclopedia or the Perry's handbook. Now in case of dense phase transport, as I mentioned earlier, the only benefit is that the low gas requirement and the low solid velocities, but it is applied to transport granular material along a short straight pipe, because we can understand the solid particles are settling in this case. It requires very high pressure, but it can be useful in conveying abrasive or friable materials, because the velocities are low, the attrition, the corrosion and all these things are lower than the dilute phase transport. In this case, so we have two extreme basically. One is the dilute phase transport, one is the discrete dense phase transport. Now in the dense phase transport, here also we can have two extreme. One is, say, the homogeneous flow, where whole cross section is basically filled with the solid particles. So a kind of a plug flow of solids can happen, and in other case there can be different scenario we call the heterogeneous flow. In this heterogeneous flow can further be classified in these three regimes. One is the discrete plug flow, that means discrete plugs of solids occupy the whole cross section. The other can be the dune flow, the sand dune like that happens. So here there will be a layer of solids that would settle, and this solid dunes would be rotating and the gas phase will flow on top of this. So there is a rolling movement of the dunes, and in between these two there is a hybrid movement of the discrete plug flow and the dune flow. So this basically gives an overview of types of pneumatic transport, starting from the dilute and the dense phase transport, its pros and cons, and a typical overview of the transport line or the total transport organization that can happen in case of dilute phase transport that we have seen. And this brings to the end of today's lecture, and the next day we will be seeing with the further different contents. Till then, I thank you for your attention.